Hi students, in this video we are going to discuss about some properties of complex signals. First let us discuss what is conjugate symmetric signal. Otherwise, what is conjugate symmetry of a complex signal. So before going to discuss about the conjugate symmetry of complex signals, we need to understand what is meant by complex conjugate. Assume that we have a number like this, that is x is equal to a plus bj. So this number is located here in the complex plane. This is the complex plane. We have a real part and an imaginary part, and the complex conjugate is nothing but a number which appears here. So what happened here is that the real part remains same, it is positive, and the imaginary part is negative. So a complex conjugate is a number which has real part is same as the actual complex number and the imaginary part is negative compared to the actual number. So we call it as x asterisk and denote it like this. A complex valued signal is said to be conjugate symmetric if it satisfies this condition: x of minus t is equal to x asterisk of t. In other words, we can say that for a signal with conjugate symmetry, time reversal has the same effect as complex conjugation. So here the actual signal x of t is time reversed to generate x of minus t, and that is same to the conjugate of the signal x asterisk of t, right? So that is the meaning of conjugate symmetric signal. A complex valued signal is said to be conjugate symmetric if satisfies the condition time reversal has the same effect as complex conjugation of the signal. The value of the signal at a negative time, maybe for example minus 10 seconds, will be equal to the value of the complex conjugate of the signal at t is equal to 10 seconds, or in the positive time axis. So that is the basic idea of conjugate symmetric signal. Now coming to conjugate antisymmetric signal. So before going to conjugate antisymmetry, we have to understand what happens if we negate the complex conjugate of a number. Here the complex conjugate is a minus bj. When we negate it, we will get minus a plus bj. So we can see that minus a plus bj is located here. Okay, so this is the negated value of the complex conjugate. Now what is conjugate antisymmetric signal? A complex valued signal is said to be conjugate antisymmetric if satisfies this condition. What is that? X of minus t is equal to minus of x asterisk of t. That means if a signal is a conjugate antisymmetric, time reversal causes the signal to be conjugated and negated simultaneously, right? So this is the time reverse signal. This time reversing is equal to conjugating and negating. See, this is conjugating and negating the signal. So that means the value of the complex signal at a negative time index, maybe minus 10 seconds, will be equal to negative of the complex conjugate of the signal at a time t is equal to 10 seconds, or in the positive time axis. So this is the difference between conjugate symmetric signal and a conjugate anti-symmetric signal. Now what happens to the real part and imaginary part of the complex signal when it is conjugate symmetric and a conjugate antisymmetric? So first let us assume that the signal is conjugate symmetric. So what is the condition for conjugate symmetry? X of minus t is equal to x asterisk of t. That means the time reversed signal is equal to the complex conjugated signal. Now we have these relations, that is x of t is a of t plus j into b of t. That means this x of t is a complex signal, right? So this is a complex signal, and any complex signal can be expressed as sum of real part and imaginary part. So we can write it as a of t plus j into b of t. Now what happens if I take the complex conjugate of that particular signal? It will become a of t minus j into b of t. Why? Because complex conjugation is nothing but negating the imaginary part of the signal. Now what is x of minus t? X of minus t is nothing but replacing t with minus t in the actual signal x of t. So we will get a of minus t plus j into b of minus t. Now our conjugate symmetry says that these two are equal. These two are equal. So we can write them on the LHS and RHS of an equation. So we can see that this is x of minus t given as a of minus t plus j into b of minus t, which is equal to x asterisk of t, that is the complex conjugated signal. So we can write a of t minus j into b of t, because that is a complex conjugated signal. That is why this minus came here, a of t minus j into b of t. Our condition for conjugate symmetry says that these two are equal. So now compare the real part and imaginary part of the signal. So we can see that when we compare the real part, we will get a of minus t is equal to a of t. So this is nothing but the condition for a signal to be even, right? We call a signal an even signal when a of t is equal to a of minus t. That means if the time reversed version of the signal is equal to the actual signal, then we call it as an even signal. Here it is a of minus t equal to a of t. So the real part of the conjugate symmetric signal is an even signal. Now what happens if we compare the imaginary part? By comparing the imaginary part, we can see that b of minus t is equal to minus of b of t, right? B of minus t is equal to minus of b of t. That is the condition for an odd signal. What is the condition for an odd signal? A signal is said to be an odd signal if time reversal of the signal is equal to negation of the actual signal or negative of b of t. From this, we can conclude that when a signal is conjugate symmetric signal, its real part will be even and imaginary part of the signal will be odd. Carefully analyze the definition. If a complex valued signal is conjugate symmetric, then the real part of the signal will be even signal and the imaginary part of the signal will be odd signal, right? So this is the basic idea of conjugate symmetric signal. What happens in the case of conjugate anti-symmetric signal? So we have studied that conjugate anti-symmetry is nothing but this relation, that is x of minus t is equal to minus of x asterisk of t. That means time reversal is equal to negation and conjugation of the signal at the same time, right? So this is the condition for conjugate anti-symmetry. So we have this relation, x of t is nothing but a of t plus j into b of t. X asterisk of t is equal to a of t minus j into b of t, and minus of x asterisk of t is nothing but negating the real part and the imaginary part. So when we negate the real part, we will get minus of a of t, and when we negate the imaginary part, we will get plus j into b of t, right? Minus of x asterisk of t is equal to minus of at plus j into b of t, and similarly x of minus t is nothing but time reversing the actual signal x of t, that is a of minus t plus j into b of minus t. Now our condition for conjugate anti-symmetry says that these two are equal. So if we equate, we will get like this, that is x of minus t is nothing but a of minus t plus j into b of minus t. Minus of x asterisk of t is equal to minus of at plus j into b of t. Now if we compare the real part, we can see that a of minus t is equal to minus of a of t. So this is the condition for odd signal, right? A of minus t is equal to minus of a of t. Time reversal is equal to negating the signal. So this is the condition for odd signal. Here you can see that the real part of the conjugate anti-symmetric signal is odd in nature. And when we compare the imaginary part of the signal, we can see b of minus t is equal to b of t. That says that the imaginary part of the signal is even. So in the case of a conjugate anti-symmetric signal, real part is odd and imaginary part is even. If a complex valued signal is conjugate anti-symmetric, then the real part of the signal will be odd and imaginary part of the signal will be even in nature. Now what happens if the signal is real, right? What happened to conjugate symmetry if the signal is a real signal? So we know that the condition for conjugate symmetry, that is x of minus t is equal to x asterisk of t, right? Now our signal is a real signal. So what is meant by real signal? Imaginary part of the signal is 0. So in our equation, we don't have this imaginary part. X of minus t is equal to a of minus t equal to a of t. The condition will be reduced to even symmetry. So conjugate symmetry of a real signal will be reduced to even symmetry. In other words, we can say that when a signal become real, the conjugate symmetry of the signal will be reduced to even symmetry. If you check the conjugate antisymmetry of a real signal, we can see that the condition for antisymmetry is x of minus t is equal to minus of x asterisk of t, and from here you can see that our imaginary part is 0 here also. So a of minus t is equal to minus of a of t. A of minus t is equal to minus of a of t. So this is the condition for odd symmetry. Otherwise we can say that conjugate antisymmetry of a real signal will be reduced to odd symmetry. So if a signal become a real signal, then the conjugate antisymmetry will be reduced to odd symmetry of the signal. When we were studying about even signal and odd signal, we have learned that any signal x of t can be expressed as a sum of even signal and odd signal. Similarly, here also any complex signal x of t can be expressed as a sum of a conjugate symmetric signal and a conjugate antisymmetric signal. Here x of t is a complex signal. So this equation says that a signal x of t, this is a complex signal. So this complex signal x of t can be expressed as a sum of conjugate symmetric and conjugate antisymmetric signal. Okay, so any complex signal x of t can be expressed as a sum of conjugate symmetric signal and a conjugate antisymmetric signal. Now what is the definition of this conjugate symmetric and conjugate antisymmetric signal? So these two signals are defined like this. XCS of t, that is conjugate symmetric signal, is defined as x of t plus x asterisk of minus t. X of t plus x asterisk of minus t divided by 2. So this is how this conjugate symmetric signal is defined, and the conjugate antisymmetric signal is defined as x of t minus x asterisk of minus t divided by 2. So please note that the conjugate symmetric signal is defined with a plus and the conjugate antisymmetric signal is defined with a minus. In the left side we have x of t and the right side we have x asterisk of minus t in both the cases and divided by 2. Let us try to add these two signal xcs of t and xca of t, that is conjugate symmetric signal and conjugate antisymmetric signal. What we will get? Of course this x asterisk of minus t and x asterisk of minus t here will be cancelled. You will get 2x of t divided by 2. So that is equal to x of t. So there is no problem in that. When we add this two signal xcs of t and xce of t, we will get the signal x of t, right? Now considering conjugating our signal xcs of t, right? So we can put a conjugate here, and we know that complex conjugate of sum of two complex numbers is equal to sum of complex conjugates of the two signals. So in that case we can take the complex conjugation inside. So you will get x asterisk of t plus x of minus t. Now if we carefully observe, you can see that this particular signal is nothing but the time reversed version of our actual signal xcs of t. So because of that reason we can represent it as xcs of minus t, right? Xcs of minus t. Complex conjugating our actual signal xcs of t will give us xcs of minus t. That means x asterisk of cs of t is equal to xcs of minus t. So this is the condition for conjugate symmetry. So we can once again confirm that our signal xcs of t is conjugate symmetric in nature. Now coming to the conjugate antisymmetric signal. So if we take conjugate for our conjugate antisymmetric signal xca of t, we will get x of t minus x asterisk of minus t divided by 2, a conjugate. So we can take this conjugate inside. So what we will get is x asterisk of t minus of x of minus t divided by 2. We have to do a small arrangement here. We have to take the negative outside. We will get minus of x of minus t minus x asterisk of t. This particular portion of the signal, if we carefully observe, we can see that that is equal to x Ca of minus t. That means the time reversed version of our actual signal x Ca of t, and we have also a minus here, so we have to represent it as minus of x Ca of minus t. So we can write x star of Ca of t is equal to minus of x Ca of minus t. So this is a condition for conjugate anti-symmetric. So this once again confirm that our signal x Ca of t is conjugate anti-symmetric in nature.